In this video, we will be discussing vapor pressure of a solution and calculations. Now, the vapor pressure of a solution, well, that's just a measurement of the number of gas particles of that liquid that have escaped into the atmosphere above the level of the liquid. Now, when you add a non-volatile solute particle, this actually lowers the vapor pressure. Fewer molecules of the solvent escape into the vapor phase. And there's a couple of explanations for this. The easiest explanation is that when you have these particles of solute in your solution, well, you don't have as many liquid particles at your surface allowed to escape. That's a great explanation, but it's completely wrong. But it's a good rule of thumb. The real reason why we have a lowering of the vapor pressure when you have a solution as compared to the pure solvent is that you have to take into account entropy. Entropy is just disorder, and all systems want to attain higher entropy or higher disorder. It is just the way of things. Now, the gas phase, you have all of these little gas particles moving about very quickly in a very disordered system, very chaotic, as opposed to a pure liquid. A pure liquid is very ordered by comparison. And then, of course, a solid is even more ordered, but we're not talking about that. When you have a pure liquid, there is this extreme drive to go into the gas phase. So you have a lot of gas particles escaping, or you have a lot of liquid particles escaping into the gas phase. However, if you have a solution, well, entropically speaking, your solution is already a little bit more disordered than your pure liquid. Its entropy is higher. So, it turns out there's less of a drive for those liquid particles to escape into the gas phase. Because it's already a little bit more disordered enough, it doesn't really need to release as many of those liquid particles into the gas phase in order to attain higher entropy. Now, Raoult's law states that the partial pressure exerted by any component of an ideal solution is equal to the vapor pressure of the pure component multiplied by its mole fraction in solution. Okay, now you've probably seen a lot of different formula for this, but this is the easiest one. What we want to do is we want to calculate the partial pressure of the solution, and for that we need to know the mole fraction not of the solute, but of the solvent. And then we're going to multiply that times the vapor pressure at that temperature of the pure solvent. So we're going to have to either look up or be given the vapor pressure of the pure solvent at whatever temperature we're working at. Although we don't have to need to know the temperature, that's going to be considered held constant. Now, this symbol, this little degree sign next to the vapor pressure of the pure solvent, that actually used to be called P plimsoll. And it used to have a line through it. And this used to be called pressure under standard conditions, which is pretty much what we're talking about. Pressure under standard conditions or pure solvent. It might be similar to something that you've seen before, such as the enthalpy degree sign, which is the enthalpy under standard conditions, or entropy under standard state or standard conditions. And it's kind of interesting, a little bit of trivia, this is derived from the old maritime use of the watermark line. And we used to hear about this about 30 years ago, and of course it had gone out of use 30 years prior to that. But it's kind of interesting information. And you're all welcome to read about it on Wikipedia. So now we want to perform a Raoult's law calculation. Calculate the vapor pressure of water over a solution made by dissolving 225 grams of glucose in 575 grams of water at 35 degrees Celsius. Now, the only reason why they've given us the temperature here is because we need to know what the vapor pressure of pure water is at that temperature, which happens to be 42.2 millimeters of mercury. All right, so vapor pressure of the solution. Well, we need to know the mole fraction of the solvent. So we need to know the number of moles of solvent divided by the total moles. Well, we've been given mass of water. So we're going to have to convert that mass, that 575 grams of water, to moles by dividing it by its molar mass. And we need to know the number of moles of glucose by dividing its mass by its molar mass. And then we need to know the total sum of both the moles of glucose and the moles of water. So in the end, we get a mole fraction of the solvent, mole fraction of water, of 0.96234. Again, this is unitless. So now that we have the mole fraction of the solvent, we're going to multiply that times the vapor pressure of water at pure water. And because we have no other units other than millimeters of mercury, the vapor pressure of this solution, this glucose solution, is actually 40.61 millimeters of mercury. And as expected, it has gone down. Because as we add particles to a pure solution, we are going to lower its vapor pressure.